Hey everybody, we are live now. What's going on? Robert Wolfert here. Welcome to another episode of Random Linux Tools Explained. And again, it's all about randomly selected Linux tools. Linux tools you can use for your day-to-day work at the Linux command line. And a challenge for me is added. I'm not prepared at all. Instead, a tool chooses for me randomly one single tool at a time, and then I want to explain this tool to you. I want to explain what this tool can be used for, how you can use this tool, and if there are some information, some tweaks worth mentioning around this tool from my experience. So again, my name is Robert Wolfert, and let's see what is the tool we are getting for today. So let's share my screen. Here we are. Let's go into the repository and let's choose a tool. Let's choose a tool via the script choose tool.sh. Let's start it. It mixes the tools and the winner is for today Ping. Great. Okay, so for the guys or ladies or friends joining in lately, let's talk about Ping now. Okay, so let's talk about Ping. And you may think Ping is a really easy tool, a simple tool. And yes, Ping is an easy tool, but not a simple tool, a really simple tool. You can do really many things via the Ping tool. So let's have a look. You know the Ping tool. You know how you use the Ping tool just to ping a host. Ping sends echo reply requests, for instance, to www.google.com, and Ping sends echo reply or echo requests. Sends echo requests and waits for echo replies. This is Ping, how Ping works. Ping simply sends one echo request per second here until you hit Control C. If you use Ping for troubleshooting, then it would be better to call Ping with an additional command line switch -n. The -n command line switch prevents Ping from trying to reverse look up the IP address every time it gets a response. Every time Ping gets a response, it tries to resolve the IP address back to a name. And if you have any problems with your network, you are troubleshooting, and then you may have problems with your network, then this lead you to false results here. So let's simply ping a remote system without resolving the IP address of every packet back to a name. Okay, so this is a command line option you should typically use if you are troubleshooting. So the next thing worth mentioning is that Ping by default pings until you hit Control C, until you terminate the ping command, until you end it. But if you want to, you can just tell the ping command you want to only send 3 packets, for instance. Just do this with the -C command line option followed by the number of packets you want to send. So ping -n-c and 3 after that only sends 3 packets, 3 echo request packets, and then here in this example we get free echo reply packets. We see in output the ping time, the round trip time, how much time did it take to receive the echo reply message from the system we are pinging to. Dash C free only pings 3 times. If you are troubleshooting and if you are working from a script, for instance, then it can be really useful to set a timeout, to set additionally a timeout, so that the ping command only waits, for instance, 5 seconds for a response. If you are using ping within a script, ping can wait a really long time after it prints out the message host unreachable, for instance. If you don't want to wait this much time, just set it via the -W command line switch. So we have, let's write this on a little dashboard. There are some more command line options, useful command line options coming in. So if you use ping, then use the -N command line switch for no resolving of IP addresses to host names. The first one, the second one, -C and a number after that. Only send N requests, lowercase w for wait, lowercase w, and a number after that. Only wait max n seconds for a response before throwing an error. Okay, and ping by default sends a request once in a second. Once a second, a request is sent by ping. If you want to send pings, not this often, not every second, just change the interval. Just change the interval. Ping sends the commands. So, for instance, ping -I and a 5, 8.8.8.8. Let's change the system we are pinging to. Now we send a ping every 5 seconds. So with -I you can set an interval. You can set an interval in seconds, greater than 1 second or lower than 1 second. Let's say I want to send a packet every 5 seconds, every half second, for instance, 0.5 seconds. Now we send 2 packets every second. Let's ping every 200 milliseconds, for instance, and we can do this. Now the ping sends really 5 pings per second until we terminate or until the number of packets to send is reached. Let's say we want to send 5 packets. 5 packets every 200 milliseconds means we need 1 single second, and you can make this interval even shorter. But this 200 milliseconds is the shortest interval a normal user can set. If you are not root on a system, you are a normal user instead, then 0.2 is the minimum interval you can use. If you want to choose a shorter interval, you'll get an error message because 200 milliseconds is the minimum here. So if you want to go further, yeah, you need to have root permissions. You need to call ping via sudo, for instance. Let's first write this to the whiteboard, -I and a number again, interval in seconds. And if I want to make this interval shorter and shorter and shorter, I don't want to ping an external system here. Yeah, I don't want to flood a foreign system with my pings. So just for now, let's ping the local host. Yeah, but within your network, you can choose every destination you want, of course. Yeah. Okay, so let's ping with an interval of 100 milliseconds. Yeah, and you can make this even shorter, until to a point where this this layout of the output doesn't make any sense. Yeah, it doesn't make sense anymore because you cannot read this. The terminal will be slower than the ping is printing out its messages. If you make this interval shorter and shorter and shorter, you end up at a point where you send ping requests as fast as your system can do it, as fast as the user space process ping can do it. And this then is a so-called flood ping. Yeah, and this can be done via the command line switch -F. And now if I call ping this way with -F, the output layout will be switched. Yeah, we will see a different output. Here I've only sent 5 packets, but let's remove this -C command line switch. And now we ping the system, the local host, as fast as we can. What you see here is perhaps, no, you won't see it, a blinking dot. The output here is organized in this way. If a ping packet was sent, then a dot will be printed out. And if a ping response is received, if a ping response is received, then a dot will be deleted. So if you have high latency, yeah, you would see some dots printed out, and after that you will see a stable number of dots. Yeah, because there are some packets on the fly, on the wire. Yeah, but as soon as you, for instance, send the 5th packet, you will get the response from the first packet you have sent. Yeah, if you, so let's terminate this. Here we won't see anything interesting, yeah, just because we are pinging localhost, and this is really fast. Let's try it only for a short time for, let's say, the 1.1.1.1. Let's change the destination. Let's send it, and now let's hit Control C for terminating or ending this. And you see here there was a dot printed out, and then after that we deleted, printed out, deleted. Yeah, as soon as a packet is sent, then a dot is printed out, and if a dot, or if a packet was received, a dot will be deleted in the output. Okay, so you can recognize here really fast if you have a huge latency, then you see many dots, yeah, but a stable number of dots. And if you are losing packets from time to time, then you will see that your number of dots will become greater and greater and greater over time. Yeah, slowly, but it will become greater. Yeah. Okay, sometimes you have networks with a lot of buffering in between. Yeah, for instance, you use mobile networks for connecting to a remote system. LTE, for instance, and with a huge bandwidth, with many or much other traffic, then you will see the buffering occurs. You will see that you get many dots printed out, and then all of them will be deleted, and then many dots will be printed out and all of them will be deleted. Yeah, so ping-f is a really great way to check how fast your ping packets, your ICMP packets can really travel the network interface, and if there are some packets lost. Yeah, so -f stands for a fluid ping, but only for root, and the smallest interval or everything lower than 0.2 is only for root. Yeah. Okay, so you can, if you want to, check if your network is overloaded or not just by calling ping-f. But do we really check if the network is overloaded? Is this a benchmark, a load test, a load check for our network? No, it isn't. Why? Just because ping packets are small packets. By default, ping packets are really small packets. And you see it here. We send packets with a payload size, the data that will be sent with the packet together is 56 bytes here by default. And with all the headers added that are needed for the ICMP packet, we are sending packets with a size of 84 bytes. Not really huge, not really a load test for our network. If you want to do a load test, then just send greater or bigger packets. Yeah, just append a greater payload. Let's talk about this. Let's say we want to ping the 11111 and we want to set a payload, a size of the payload of 1000 bytes, for instance. Ping-s 1000. We don't need to be root for this. Yeah, everyone can send larger packets, and now we send packets. Let's terminate it by pressing Ctrl+C. Everyone can send packets greater than the default of 56 or 84 bytes here. Now I have sent 1000 bytes per packet as a payload, and this adds up together with the headers to 1028 bytes here. Yeah, we can make these packets bigger and bigger and bigger and bigger until to a point where it doesn't make sense. It doesn't make really sense to make these packets bigger. Where is the point? The point is the MTU, the maximum transfer unit of your network connection, of your network interface. If you want to see this, yeah, just use the tool IP, for instance, for this. IP link will show you the link layer of your network interfaces. And you see here we have for the ETH0 interface, for the first Ethernet interface here of the system, an MTU of 9001 bytes. This system is configured with jumbo frames. By default, a default Ethernet interface will have an MTU of 1500 bytes. Yeah, but here we have an MTU of 9001 bytes. If we would send packets greater than this MTU, then our network stack will simply fragment these packets and we wouldn't see any difference here. Yeah. So let's imagine. Now let's only imagine our our MTU would be this default of 1500 bytes. So the biggest or the largest packet size that would make sense would be 1500 minus the header size, and the header size here is 28 bytes. So send 572 bytes payload with each packet to 8.8.8.8, for instance. And now you see we are sending really 1500 bytes or 1500 bytes, big or large packets, and Google won't send the whole packet back. Yeah, we will get only 76 bytes back. But if we will combine this with the flute command line switch, I don't want to do this now, yeah, then we would really do a load test on the wire, yeah, just because we are sending the largest possible packets with the largest possible rate from this single process. Yeah, so that could really put some load on the wire. If you want to do a real load test, you would start this command line multiple times. Yeah, let's try this out, not with the -F command line switch, but without, and let's make the packet size even larger. Yeah, and you see now we get a different output here. We get now a different output here, and the output is fragmentation needed. What's the thing here? What's going on here? If you are on a system, yeah, let's say you are here. This is your local system. So, and now you want to reach a remote system. You want to reach a remote system here. This is the remote system. This has an IP address. So, okay, you want to reach this remote system from your local system, and you have multiple networks your packets has to traverse through. Yeah, so multiple networks are here, and between the networks there is a gateway. Yeah, here we have a gateway. Let's write gateway or firewall, just as you like. In between, this is a gateway. Okay, different color, orange. Great, orange is the gateway. The next gateway in between here, the next gateway here, yeah, and then you have your remote system on the other side. So, and now let's say we have here a network with an MTU of 1500 bytes. Here again we have an MTU of 1500 bytes, and now we have an MTU of 1400 bytes, for instance. Yeah, because this is a DSL connection or something like that. We need some overhead for the network stack, whatever. Yeah, we have different MTUs. So what's now going on if we send a small ping packet? If we send a small ping packet, yeah, a small ping only with a size of, let's say, 84 bytes. Yeah, nothing happens, everything works, yeah, because the 84 bytes will traverse every single network here. Now let's say we don't just ping a system, but we transfer data. We send a large amount of data to a system via an FTP, put via an SCP, an rsync, and WebDAV, whatever. You send a huge amount of data to a remote system, and your packets are packed or are sized as your MTU allows you. Yeah? Now, what's the problem now? As soon as the packet reaches this gateway here, this gateway cannot route this packet unmodified to a remote IP. Yeah? It won't work because we have an MTU of 1400 bytes here. What can this gateway do? Two things. First, this gateway could simply fragment this packet on its own. Yeah? It could send, simply spoken, 2 packets, 1400 bytes plus 100 bytes. Yes, we have the headers and so on, but you get a point here. The gateway could split the packet into parts and then send each part of its own. But most of the time, the gateways won't do this. Yeah? Just because with fragmentation, if you use fragmentation, then there are some problems you are introducing with firewalls, with packet filters, for instance. Or you could simply overload a gateway by just sending large packets to this gateway, and this gateway would need to fragment. Yeah. Instead, the gateway won't do anything but send an error message back to the requesting system or to the sending system. And the error message here says we need fragmentation. Fragmentation needed. Yeah, and fragmentation needed to the size of 1400 bytes in this example. And now this system knows, okay, I need to fragment, and from now on this remote system will only get packets with a size of 1400 bytes at most. Yeah, and this then will reach the destination. Okay, so now it could be a problem here, or do you see a problem here? The problem is with this gateway here. Let's say you send a packet. You send a packet, these 1500 bytes, and the destination IP, the DIP, is the IP of the remote system. Yeah, the destination IP is this IP address. Let's color this. Yeah, IP, or let's simply write IP remote. We send a packet to the remote IP address, and then as an answer to this packet, we get a fragmentation needed packet from the gateway. From IP gateway. Do you see the problem here? Yeah, the gateway here, if this is a firewall, for instance, or this gateway here, if this is a firewall, for instance, will see an outgoing packet going to a remote IP, and then it will see an incoming packet coming from a completely different IP. Yeah? And if the gateway or the firewall cannot match these two packets, yeah? If the firewall cannot say that the incoming packet belongs to the outgoing packet, then perhaps this packet will be dropped. Yeah? So this could be a real problem, and this is or was many times a real world problem I have seen. Yeah? And it looked like this. You are sitting on a system, you can simply ping a remote system that works perfectly with a low latency and so on. But as soon as you do real traffic, as you open a website to the web server, to destination IP, if you transfer data, whatever, then the connection slows down a lot. Yeah, and sometimes it hangs and nothing happens just because these fragmentation needed packets were interrupted. Yeah, you have here a break because this gateway won't let this fragmentation needed packets in. Yeah, and you can see, or yeah, you can recognize this type of problem just by pinging the remote system and by sending packets with a size matching your MTU. Yeah? And if I, for instance, I see on my system here, IP link, that I have an MTU of 9001 bytes, yeah, and I could simply try to send these large bytes to a remote system, but the remote system won't ever get these huge, large packets, yeah, just because this MTU is only valid for my local network here. After the gateway, there will be typically a normal a default MTU of 1500 bytes. Yeah, and I can see this simply by sending packets greater than this 1470 bytes, 72 bytes to a destination 8.8.8.8. Yeah, and you see this works 1472. Yeah, so in sum, the MTU is reached. Now make or add one single byte, and you see you'll get an error, fragmentation needed, and we get this error from, not from the system we sent a ping to, but from this system, and this system is the first gateway here. Yeah, so we send a ping, a packet greater than this 1500 bytes. This gateway responds fragmentation needed. Yeah. Okay, so this is really a great way to check if you have any MTU problems. If you have MTU problems, we don't have MTU problems here. Yeah, we don't have MTU problems here because we receive and we see this fragmentation needed packet, yeah, with the MTU set. But if we won't see this fragmentation needed packet, yeah, then we won't get any answer, and our system wouldn't even know that we need to, or that it needs to fragment its large packets. Yeah, so this is really, really important to check if you have networking problems and your pings works, but your other network traffic doesn't work really stable. Yeah, check the fragmentation. Check if fragmentation works, if the fragmentation needed packets are coming. Yeah, so let's say with -s, you can set the size of the payload to size bytes. Yeah, just to check an MTU, for instance. Now let's go to the last command line switch here. I want to show you the last command line switch is also really great for troubleshooting. The last command line switch is the command line switch -t. What can this command line switch be used for? This command line switch can be used for to check what are the gateways on the way to a remote system. Perhaps you know the trace route command. Perhaps you know this trace route command. Yeah, trace route 8.8.8.8 would print out if installed. Yeah, it isn't installed here. If installed, all the hops that must be traversed until your packet reach the remote system. Yeah, and sometimes traceroute works, sometimes traceroute doesn't work, because traceroute uses by default some randomly chosen upper UDP ports, and sometimes you can use traceroute via TCP or different ports, but you can use ping to model the behavior of traceroute. The way traceroute gets the next hop on the network is simply by just sending a packet and setting a TTL for this packet. Let's say I send a packet with a TTL of 1, for instance. Or let's say by default we send a packet with a TTL of 64, for instance. Yeah? Every gateway on the path has to reduce this TTL by 1. The TTL is not a time to live, but the hops to live. It should have been named HTL, hops to live. And a gateway that gets a packet with a TTL of 0 isn't allowed to route this packet further. Yeah? Instead, it has to report this as an error message. The TTL is exceeded. Yeah? Just to avoid the bad things that could happen if we had some loops, some routing loops, for instance. Yeah. So, and therefore the TTL is set for every packet on the internet, every IP packet you see anywhere. Yeah, a TTL is set. And if you set here a TTL of 1, if you send a packet, then the first gateway on the path will reduce this TTL by 1 and gets a TTL of 0 as a result, and then it responds with an error message. Yeah? So you're sending again a packet to the remote IP, but you will get an error message from the first gateway of the system, and this then tells you TTL exceeded. Yeah? And you just have to look at the IP address that sends you this TTL exceeded message, so that you know this is the first hop on the path. Yeah, and after that, just send the next packet with a TTL of 2. Yeah. You have a TTL of 2, and the next hop will respond. Yeah, TTL of 2. Here in this first example, the first hop will respond. This is this first gateway. Then we send something with a TTL of 2, and now the second hop on the path will respond with a TTL exceeded. Yeah. So, okay. I hope you can see this. Let's verify this. Yes. Here the banner. Yeah. So the second gateway answers here. Okay, let's model this. Ping -t sets the TTL. -t sets the TTL, -t1, and let's ping the 88888 or 8888, only 4 8s here, and you see no one answers. Okay, let's try this with a TTL of 2. No one answers. Oh, let's try this with a TTL of 3. No one answers. Okay. 4, 5. Okay, we don't see any TTL exceeded message here. It has to do something, I think, with the AWS cloud this system is running in, and with the security groups they are configured. Yeah. Okay, you see it. If you set the TTL to something larger than 5 here, yeah, if we cannot recognize the hops 1, 2, 3, 4, and 5, but we can recognize or detect the hop with the number 6. This is the hop with this IP address. Yeah, the hop with the number 7. Let's send only one single byte here. Yeah, the hop with the number 7 is the hop with this IP address. The hop with the number 8 is the hop with this IP address, and so on and so on. Yeah, so you can really go step by step until you will reach the system. Let's try out how many hops we need to the 8.8.8.8. Yeah, let's TTL of 15. We'll get a response. Let's take the 12. No response. 13. No response. 14. Here we have a response. Yeah. So we have 14 hops or 13 hops to go through until we reach the 8.8.8.8. Yeah. So this is the last command line switch I want to show you. Yeah, TTL is the number of hops. So set max TTL number of hops before TTL exceeded message. And the last thing here that is great about ping tool is that the ping tool gives you a response for the success of the ping itself. Yeah. So if you want a script, for instance, and if you want to see if you can reach a system, the 1.1.1.1, can we reach a system? Then you can, of course, if you want to try to search the output of the ping command, yeah, to recognize if the ping was successfully or not. But ping sets a return code. If you don't have any output here, yeah, let's throw away the output to Dave null. Yeah, and if we don't have any output at all, we can simply try or have a look into the return code of the ping command. Yeah, the variable question mark always contains the return code of the last command. The last command here now was the ping command, and the return code of 0 means ping was successfully. Let's try to ping the 8.8.8.8 C1 8.8.8.8 and successfully. Let's try to ping the 8.8.8.9. Let's wait a few seconds, and in a few moments you will see an error message perhaps. No, we won't see an error message. We have thrown away the output data stream here, but the return code says that this ping here wasn't successful. It wasn't successful. Return code is 1 here. And if you want to go really fancy, you can use this information to combine the ping command with a different command, for instance. Yeah. Let's say I call ping this way. And then I just print out succeeded, but only if this ping worked. If this ping won't work, 888.9, and I don't want to wait this long. I just want to wait maximum 2 seconds here, and after 2 seconds I will get an output. No, I will get no output, just because this comment separator here, if you really want to go fancy, only starts the second command, the command after these pair of ampersands, if the first command line or the first command gives you a return code of 0. If there is a return code different than 0, other than 0, then the second command won't be run. If you want to have it the other way around, you can do it with 2 pipe signs and then just print out not succeeded, for instance. Not succeeded, and let's ping a system that is reachable, and now we don't get this output not succeeded. So this is also a really great and useful feature of ping, that ping sets a return code, and this return code shows you if the ping was successfully or not. So you can not only just use ping for pinging a remote system and checking if DNS is working or something like this, but you can use ping for doing a lot of other checks, a lot of different checks. You can put load on your network by doing a flute ping and by sending really large packets with a large MTU. You can see if you have MTU problems along the path to a remote system, just by trying to reach your local MTU with the packet size of the packets you send. You can see the hops of the path to a remote system just by playing around with the TTL. And you can use the ping tool really great for scripting, just because the return code of the ping tool is or shows you if ping was successfully or not. It's a really powerful tool. If you have any comments to this, if you have any questions further, please let me know within the comments. I hope you enjoyed this short lesson, or this not so short lesson. See you next time. Robert.